Hi friends, welcome back. So a set is just a well-defined collection of objects, and these objects are called elements or members. So what we in the formal logic cares about is the precise rule of deciding whether an element belongs to a set. So for Lean, it models a set as a membership test, not a bag of elements. So depth set in MATLAB's approach is for that idea. So a parenthesis will hold alpha, the type of element you are ranging over, and type U for alpha just means that alpha is living in the type universe called U. And the arrow alpha to prop just means that one element in and one true or false statement out. So that is the function type. So it's different from the fat arrow on the lambda line later. So a prop in Lean is just a statement that you can be proven to true and false to apply the tactics with. So for example, all integer here, it takes in, it is a set of integers. So it's a set applied on int. Alpha here just replaced with int. And column here is just means the return type of this. And we have a function statement in Lean here. It's just like a JavaScript arrow function. It basically says that if you're taking in, so the body of all integer is a function of that takes an n and return a proposition about n. If you can prove this proposition, which is an equality, you can prove that the element is in the set. So if you apply all integer to n directly, you will get a proposition directly that you can prove. Notice that Lean never forces you to treat the prop as a membership condition. It's up to us to decide that this kind of proposition is specifically about membership. So the semantics of types is up to us to define. So next, MATLAB define a namespace block for set. So namespace is just a container for definitions, so that you can call set.m to refer to this definition. So after that, MATLAB adds a protected def mem. So protected just means that you have to use the namespace prefix in order to call this function. So the return type of mem is just another proposition. So it's basically a wrapper for you to apply your set actual function on an element. But what is the symbol of A in S, which is the mathematical concept? So this is actually more complicated than we think. So this notation is the built-in syntax in Lean's kernel. And then the notation is binded to a type class called memberships, which is also in the kernel, which is basically encapsulation for method in Lean. And notice that the outparam here on the element types, it means that it can be ignored in usage, and Lean, which is inferred from it. So this is the preparation work. But in order for our set to use this notation, we still need to do one more thing. And that is to implement the type class on depth of set by using the instance block here. So notice here, alpha is bounded by set alpha on the right. So whenever that is allowed in set alpha, it was allowed for alpha. So this Lean infer that from the set. And by using the angle bracket here, we put the implementation for the only method of this type class, which is m. But if we have multiple methods for a type class, then we have to implement them one by one, as shown below. So now we can use this notation like this because the type class implementation, and notice that it constructs a proposition with A in S nicely. And then you can use this for other examples, for example, like and in all integers. So this is the full picture of the Lean's modeling of set. So first we define a function type constructor, then the prop return and wrapper, finally binding the notation of the mathematical in operator to set. So now we look at ternary instead. So notice that it immediately gives you a container story. So we model set using a structure directly. So a square bracket makes a container structure, which allows you to use the in operator. So then we can use the in operator for every specific set to determine is membership law. So for example, we can model empty set by inheriting from set first, and then we use a law to specify the membership function, which is the no member method. And it says that for every x is not in itself, so nothing can be belong to the empty set. The law is just a requirement that every instance of this structure must be satisfied. Similarly, the union of set follow the same patterns. Its law says that if x is in self, which means in the union of A and B, then it's either in B or in B. So this is how we model set in both languages. Can you see the difference? So I hope you enjoyed this video and leave a comment if you have any problem running the scripts. So in the next video, we'll talk about subset, and please subscribe and see you in the next one.